Okay, so we're going to go through our review sheet. You should have already tried it out, and we're going to go through it to make sure you're right. If not, good listening skills, I suppose. So let's look at number 1. A wave travels from one medium to another, and the wavelength decreases. What happens to the velocity and the frequency? Well, one thing we know is that the frequency is always the same. The frequency will never change, no matter how the medium changes. Now, we also know that v is equal to lambda f. If this stays the same, and the wavelength went down, well, that means the velocity went down. So velocity goes down, and the frequency is going to be equal. The Sears building in Chicago sways back and forth with the wind with a frequency of about 0.1 hertz. What is the period? So, the period is how long per sway. And if it's this many, so remember, it's 0.1 cycles per second, right? So how do I get how many seconds per cycle? Well, you just got to do the reciprocal of it, right? So 1 over 0.1, which is going to be 10 seconds per cycle. Whatever. It takes 10 seconds for it to sway back and forth. Starting with the wave below, sketch the following wave with twice the amplitude. Well, it's going to look like it's going to be taller, right? Taller and deeper. A wave with twice the frequency, so I'm going to go back to this one here. So twice the frequency means it's going to go up and down twice as much. So it's going to go. Sound effects are optional. It's going to look something like that. Twice the wavelength, it'll look like that. It'll be wider. Ta-da! Right? Because wavelength is this distance here. Frequency is how many cycles you get in per second. So, ta-da! If a wave on a drum looks like this, boom, boom, push. Let's sketch how the wave would look like if the drum were hit harder. Well, if it's hit harder, that means that the amplitude is going to go up. If the amplitude goes up, it's because it's got more energy, so it's going to look like that. Ta-da. Sketch the results of these pulses. Alright, sum of A plus B. Okay, so if we added them together, we're going to get a bigger one here and a flat one over here, because these parts are going to be constructive and these parts are going to be destructive, because they're opposites. The pulse below is reflected from a rigid medium. Sketch the reflected pulse underneath. Okay, so here's the block. So basically, what does it look like after it bounces? It's going to look. A favorite but shark-infested surf spot has waves with wavelength of 10 meters. Nice. I mean, radical. A wave passes by the surfers with a speed of 2. How long between waves must the surfers have to wait? Surfers don't wait, man. Okay. So what do we know? We know that we're going to be using a lot of v equals lambda f here. Alright. A wave passes by the surfers at a speed of 2. That's the speed. So 2 is equal to lambda. We know the wavelength is 10. 10 times f. So what is f going to equal? F is going to equal 0.2, right? 2 divided by 10. Quick maths. That's in hertz. So how do we figure out the period, right? The period, how long they have to wait, is going to be the reciprocal. 1 over 0.2 is going to equal 5 seconds. Microwaves with a speed of 3 times 10 to the 8 are too fast for surfing. The more you know. But energetic enough to cook food. Most microwave ovens operate at a frequency of that. How long is the wavelength of these microwaves? Ooh. So what we can do is the same kind of formula. So we got 3 times 10 to the 8 is over there, and that's going to equal the wavelength, which we don't know, times the frequency, which we do know. It's going to be 2450, but this is in megahertz. Megahertz is million, so times 10 to the 6. Alright, so you can do some simplifying here. But anyways, we're going to type it into our calculator. Divided by 2450. So we're going to get a lambda of about 0.12 meters. So that's about 12 centimeters. And you can calculate, you can actually measure this in a microwave. We saw a video on it in the last spring, if you remember. But, I mean, that was years ago. If a speed of sound in air is 340 meters per second and the wavelength of a sound is 5 meters, what is the frequency of this sound? What is the frequency of the sound that moves water? Oh, it's double hitter. Okay, so we've got V is equal to lambda F. There's our speed. Our speed is 340, and that's going to equal our wavelength is 5. So what is the frequency? And the frequency is going to be 340 divided by 5, which is 68. Almost nice. Hertz. What's the frequency of the sound as it moves into water? It's going to be 68 hertz because frequency does not change. But what does change is the speed. The speed goes way up when you're in water. Sound travels faster in water. So, since the frequency stays the same, but the speed goes up, the wavelength also goes up. So now let's look at number 10. AM signals are broadcast from the frequencies 550 kilohertz and 1600 kilohertz. FM frequencies are between this and that. All radio waves travel with that. What's the range of wavelengths for both there? Alright, so let's just do AM first. Not hard. So we're using V is equal to lambda F again, over and over again. It's a very important equation in case you haven't figured it out yet. So let's take 550. So we have 3 times 10 to the 8 is equal to lambda, which we're looking for, times F is 550 kilohertz. So that's 550 times 1,000, 10 to the 3. Alright, so for this, we're going to take 3 times 10 to the 8 divided by 550 times 10 to the 3. Right? If you don't have a good calculator, you can just type in that many zeros each time. 545 is what we should get. Let's just round it to the nearest whole number. It's good enough for this. 545 meters. So now we're going to do the same idea. This number will be the same for all of these. Lambda times 1600 times 10 to the 3. Okie dokie. Well, I can cheat a little bit here, because the calculator has these numbers remembered, sort of. So we're going to get a lambda is equal to 187.5. So anywhere between these, 188, we should just say, whatever. And that's going to be your AM range, and your FM range is going to be a little different. So we're going to have 3 times 10 to the 8 is equal to lambda times 88. Now it's megahertz, so that's going to be times 10 to the 6, because we know our metric prefixes, hopefully. So what is that? So that's 88 times 10 to the 6. So that's going to be 3.4 meters is our wavelength. Oh, that's not equal. Alright, and then one more time. This time we're doing 108 times 10 to the 6, because megahertz. So 108 times 10 to the 6. So we're going to get about a 2.8 meters. Ta-da! You can do this with your favorite radio station. Isn't your favorite KRUD? Or is that just the music it plays? Anyways, what's the wavelength of a radio wave from an AM station broadcasting at 750? Find the wavelength in meters and kilometers, compare it to some familiar object of similar length. Okay. So it's going to be 3 times 10 to the 8, because that's all radio waves forever, at least in this universe, is equal to lambda times 750 times 10 to the 3. So lambda is going to equal 750, 400. So that's 400 meters, which is also 0.4 kilometers. So how long is that? Well, here's the easiest thing I thought of. This is one lap on the track. School track, right? If you run around one time, that is one wave for that radio station. Do you remember being in school and running around the track? Back in the dark ages, it felt like. Anyways, a standing wave in a clothesline has 4 nodes and 3 antinodes. Alright, so the clothesline is 12 meters long and is vibrating at that many per second. Right? What does this mean? This means that's the frequency. What's the speed of the wave? So let's draw a picture. Oh, that's too many. So we have 4 nodes, 1 node, 2 node, 3 node, 4 node. Alright, so this part doesn't exist. Alright, so this part is 12, alright? And it's vibrating at 0.5. So what's the speed? Well, let's think about it. The speed of the wave is equal to lambda times f. The lambda, if the whole thing is 12, I need to know what one wave is, right? One wave, we're going to do 2/3 of 12 because we need 2 pieces out of 3. Surprise, surprise, it's 8. Feel familiar at all? Times the frequency. The frequency is 0.5, so that means the V is going to equal 4 meters per second. Alright, hopefully you had as much fun as I did going through this. We'll see you tomorrow for Zoom. We'll do some more practice, and pretty much on Monday next week you're going to have a quiz on, the stuff we've done with waves so far. Alright, we'll see you later.